In today's notes, we're going over a topic called linear regression. So we've probably mentioned this a little bit, but this is a way to do a trend line that is the mathematically calculated best fit trend line for a scatter plot or a set of data. So rather than doing a hand-drawn trend line, which is not precise or perfect, this isn't perfect either, right? It's an estimate, but it's the best possible estimate. You could think of this line as being the average of all of the dots. So there's a second topic for today, which is association and causation, but there's a separate video linked for that on Canvas. It uses a different notes page, but it's a good reference for the notes for that. So linear regression, we're going to start off by reviewing scatter plots and trend lines. So we have a scatter plot here with a blue line. I'm not positive if this is a trend line or the line of best fit, but we're going to just go with it and say this is the linear regression line of best fit. We're told that the equation is y equals 3.48x plus 0.76. And this graph is relating the cost of ingredients that we use in a dish or like in food versus how much we can sell that for. So you could think of this as like the markup that a restaurant has. They pay a certain amount for their ingredients and they sell the food for a higher price. So first of all, we're going to start with what is the predicted sale price of an item that had ingredients that cost $1.50. So this tells us we're looking at X because that's ingredient cost. So we go to 1.5 on the X and we scan up, and then the first thing we find is this black dot. So the really important thing to get down with trend lines or line of best fit is that once we've drawn this blue line, the black dots have zero value. We do not want to ever refer to any one of these black dots once we've drawn the blue line. So we're going to pretend that black dot doesn't exist, and we're going to continue on up to find out where our line is at 1.5. So we can see that that matches up with a sale price of $6. So the explanation here, the important thing is that we're not going to look at this black dot that's at about $5.25. Instead, we're looking at the blue line. Just because one time paying $1.50 for ingredients resulted in a sale price of $5.25, that's not our best estimate based on all of the data. So using all the data together, our estimate is $6. What is the predicted ingredient cost of an item that has a sale price of $7? So this time, sale price is Y, so we're going to look at sale price of 7, carry on to the right, and just like before, we find a black dot, but we want to ignore that black dot. We don't want to take that into account. Instead, we want to look at where our blue line is right here, which is pretty close to the black dot, but the blue line is what we care about. It's about halfway between 1.5 and $2, so I'm going to say it's about $1.75. I can't be perfectly precise because I think it's just slightly more than halfway, but it's about $1.75. So again, we want to focus on the blue line, pretend all the black dots don't even exist. The slope of the line is given to us as m equals 3.48. And we could say that that is dollar sale price, so that's sale dollars versus cost dollars. And what does it represent? It's telling us basically the multiplier of how much you spend on the ingredients, what you multiply it by to see how much you're selling it for. So for every dollar that you spend on ingredients, you're selling it for about $3.50 or 3.5 times as much. What is the y-intercept of the line of best fit? So we can see here that it's a little less than $1, and from the equation, we're told that the y-intercept is $0.76. So what does that mean in this situation? It says that if we spent $0 on ingredients, so we bought nothing, we could sell that nothing for 76 cents. Does that make sense? No, but we're also never going to sell $0 or zero things because nobody would buy it. So this is kind of an irrelevant data point. We know that in reality, if we sold $0 worth of things or sold nothing, we would make $0. But notice that the trend line doesn't go through 0, 0, and that's totally okay because the 0, 0 dot here would just be like any other one of these black dots. It's a single data point. It doesn't control where the line goes as a whole. So it turns out that the best way to represent these dots is by saying it's 3.5 times as much, but it's also got a vertical shift of 0.76. So it does make sense in terms of being an estimate. It doesn't make sense in terms of a real world, like using this to sell $0. Just like it wouldn't make sense if we went and continued the line into the negatives and said we're going to sell negative 50 cents worth of ingredients. So we know that these parts of the graph are kind of not real anyway, so we can kind of ignore those. Okay, we're going to skip over the association causation section right here because, like I said, that's in a separate video. And we're going to skip down to linear regression. So linear regression is something we use computers to do because it takes an incredibly high amount of work and is very tedious to do by hand. I'm talking like hours worth of work, not like minutes. So this takes a really, really long time, and we don't want to do that. So instead, we use Desmos or a different computer program or calculator in order to do it for us because it can do it instantly. So when we do a linear regression, we end up with something called a line of best fit. So a line of best fit is like a trend line, but it's the absolute best trend line that's possible to make. And if we make a line of best fit in a TI calculator, Desmos, Microsoft Excel, Google Sheets, or any other program, they will all give us the exact same line because they're all calculating it in the exact same way. So we get two things out of a linear regression. First of all, we get a y equals mx plus b equation. So it finds the slope and y-intercept that best represents our data. The other thing we get is a value called r. We get r equals some number. R we call a correlation coefficient. It tells us how correlated the two data sets are, the x and the y. The number ranges from -1 to +1, and it tells us how closely it fits the data. So we have kind of a different way to think of it. It's -1 to 1, but what I want us to think of it as is it's really from 0 to 1. So if I have an r value whose absolute value is between 0 and 0.25, so this would be either positive or negative 0.25. That's what the absolute value symbol means. So this we would call no correlation. And in terms of why I think of it as 0 to 1, this is like 0% to 25% correlated. So it's the two data are correlated by less than a 25% factor. If we have an r value whose absolute value is between 0.25 and 0.75, we would say that this is a weak correlation. So anywhere from 0.25 to 0.75 or negative 0.25 to negative 0.75, that's like a 25% to 75% correlation. So we're using these as kind of generic breakpoints, but really it depends on the industry that you're working in and what the data that you're using represents. So for things like automobile reliability, you may care about things where the R value needs to be 0.98 in order to be statistically significant. Whereas if you're making medication that could help somebody with a heart problem, maybe if it's correlated at like 0.4, that's good enough that it's worth trying that medication because it might help. So these numbers take with a grain of salt. They're not like universal, but this is what we're using within this course to kind of set these breakpoints. So the final range would be 0.75. R is between that and 1.0. So this is between 75% to 100% correlated. We're going to say that has a strong correlation. And in terms of a scatter plot, remember that the strength has to do with how close the dots cluster around the line. So in our warm-up, these dots were very closely clustered to this line. So this probably has a correlation coefficient of like 0.95 or something really high. I don't think they told us. No, they didn't. Okay. So we have this graphic organizer to help us with what the R values are. This is a good summary over here, and we're going to fill in that information in this graphic organizer. So from 0 to 0.25 in both directions, we say has no correlation, or at least not a linear correlation. From 0.25 to 0.75 in both directions, we're going to say is a weak correlation. So these two are both weak. And then above 0.75, we say is a strong correlation. And those will often be in the like 0.9 to 0.99 range. They're usually very high numbers when we see strong correlations. As a side note, if you have 1, which would be a perfect correlation, that would be 100% correlated. That would be like if you took one of the tables that we've used that define all the points on a line, and we enter that into a linear regression. So if every single dot falls perfectly on the line that it calculates, then that means that those points are not a scatter plot. They're just points from a line. So then on the bottom end here, we have the idea that if we're going this direction from 0 to +1, these are positive correlations. So in this range here would be weak positive from 0.25 to 0.75, and from 0.75 up to 1 would be strong positive. So we use the combination of the word above and the word below in order to classify. And when we talk about positive, or on this side negative, what that means is that our slope of our trend line is going uphill or downhill. So this is like a positive slope, and this is a negative slope on our line. Okay, so now we're going to move over to using Desmos in order to do the linear regressions and learn how to do that. It's incredibly simple to do, and they made it even easier to where it's hard to get it wrong. So I'm going to open up Desmos and OneNote side by side here, and then we'll do a couple of these as examples. Okay, so I've opened up OneNote and Canvas. The reason I've opened Canvas is if we go here and go to Desmos, this calculator is not the same as what you get to use on Star. So whenever you're using Desmos, if you want, you should use the version that you get on Star and in Aware, which is a little bit more restricted than this one. So I can tell this is the normal Desmos because up here it just says Desmos Untitled Graph. If you go to Canvas under Course Resources, you can find right here Desmos Graphing Calculator with Star limitations. So if you launch this one, you see that it says Graphing Calculator Texas version, and it has a green banner. So you need to either launch this through Canvas, or if you're on Desmos, you can go to the main Desmos Calculator site, go to Math Tools, Test Practice, and then before clicking Graphing Calculator, you have to go up here to Choose Assessment at the top. Under Choose Assessment, we scroll down to Texas, Star, and then open the Graphing Calculator. So this one has a black banner like the normal Desmos, but it says Texas version at the top, just like this green one says Texas version at the top as well. So whichever way you navigate to it, make sure that you're practicing using this version so that it's what you're going to see on Aware and on Star. Okay, so how do we do linear regression? We're given this problem in OneNote of a guy, Hugo's Hot Dog Hut, has been advertising specialty items. During a 10-week period, Hugo kept a record of the number of advertisements and the number of specialty items sold each week. So we have his ads over here and his items sold over here. We need to get this table into Desmos. So if you're not aware, you can click on this little plus, which says Add Item in the top left, and one of the options is to add a table. So we're going to add table, and we get an X and a Y column, just like on this table. If our table was sideways, like the one down here, remember that X is always the top row and Y is always the bottom row. So we would go across this row to make our first column in the table and across the bottom row to make the second column. So let's put in our table values here. So you're going to type these in, and the most important thing, the number one thing you could screw up here is if you mistype the numbers. So after you're done typing them in, make sure to go back and compare them with the original list. So I'm going to type all of these in, and then I'm going to go back and do a double check to make sure that I didn't mistype anything. So 6, 20, 1, 14, 25, 16, 28, 18, 10, 8, 150, 310, 100, 160, 280, 200, 400, 250, 120, 150. Perfect. So these are all correct. If one number, I'll show you after we do it, but if one number is wrong, it can cause a big error in your results. So it used to be that the way we did a linear regression was to type y1 is approximately mx1 plus b. And this is good because it tells us m and b, and it's basically just slope-intercept form where we replaced x and y with the names from the table up here, x1 and y1. And we changed the equal sign to this tilde character, which means approximately. So this is nice because it gives us our slope, it gives us our y-intercept, it gives us the r, or correlation coefficient. It also gives us r squared, which we want to ignore. That's for statistics. We don't want to use that one. So we have m, b, r, and that's everything that we need from a linear regression. But the Desmos and Star has made things even easier now. You don't actually need to type this in. You still can. And there are benefits to knowing how to type that. Like if M or B doesn't have enough decimals, you could come down here and type those letters and get more decimals if you need them. But we don't need to type that. Instead, they added this nice little magic button. Anytime you make a table, once you fill in the data, this magic button appears that says Add Regression. So if I click on that, it just creates the linear regression equation for me, and I get my line of best fit and my R value without having to type in any special stuff. It also has a drop down with all different kinds of regressions. So this year we'll be doing linear regression, exponential regression, and quadratic regression. So all of those are here, and you can change it just by clicking on this drop down. So if I wanted a quadratic regression or a exponential regression, I can just change those, although they wouldn't be a good fit because this is a linear data set. Okay, so we got our equation and the R value. We should now be able to answer the stuff over here in OneNote. But before we do, let me zoom out a bit. So we can see that as I was plotting this, or filling in this table, we actually also were creating a scatter plot. It was just off screen because the numbers are so big that I had to zoom out to see them. I can turn on and off the scatter plot by clicking on these this green circle with the white dots, and it makes it go away. And I can turn on and off the linear regression line by clicking on the blue line right here if I had a reason that I want to hide one or the other. Usually I would hide the dots because remember, as soon as we've drawn the blue line, the dots have no value and we never want to refer to them again, so hiding them is actually beneficial. Oh yeah, and before we go back here, what happens if I typed a number wrong? So let's say instead of 250, I accidentally typed 350. We had 10.37 and 60.55. If I change that, then that actually didn't change that much. The change is often a lot more drastic than that. So this only went off by like 0.2 and by 2 here, which still is going to make a difference if you have to type an answer into either Delta Math or Aware or something. You'll get the wrong answer if you have a wrong number. Okay, so back to OneNote. We have first calculate the correlation coefficient. So we can see here that the R value is 0.9235. It doesn't tell us what to round to, so since this number is smaller than 1, I'm going to keep 3 decimals. We say that's the 1,000th place. So we're going to go 0.92, and then since we're stopping at this 3, we have to check the next number. Since this is 5 or more, it's going to bump the 3 up to a 4. So we get 0.924. This data has, we can see 2 things about the R value. It has a positive R value, I don't know why I'm trying to write with my mouse. I could use my drawing tablet. So it has a positive R value, and since this number is bigger than 0.75, it has a strong correlation. So remember, going back to our graphic organizer, 0.92 is about right here on our graph. So that is strong and that is positive. Those are the two things that characterize that. Okay, then it wants us to write the equation for the line of best fit. Since it doesn't tell us what to round to, we're going to go ahead here and keep 2 decimal places. We call that rounding to the nearest hundredth place, or to the nearest hundredth. So we're going to do y equals 10.37. And then remember, since we're stopping at 7, we check the next number is a 2, so we don't need to bump this up. So 10.37x plus, then we have 60.55, but the second 5, we look at the next number, and there's a 6 after it. So we have to bump this one up to a 6. So that's our equation for the line of best fit. And then it asks us, Hugo has determined he can only afford 11 advertisements per week. Based on the equation of line of best fit, how many specialty items can he expect to sell? So in this case, since it's based on that equation, we want to use this rounded version of the equation to calculate the answer. We could get a more precise answer from Desmos, but in Delta Math, when it asks you to do this, it's expecting you to use this rounded equation and plug in the value. Since advertisements was the x variable, we're plugging in 11 for x and doing plus 60.56. And then we probably want to go ahead and back to Desmos, since we have it open already, and do 10.37 times 11 plus 60.56. So we end up with 174.63. He can't sell partial items. This is discrete. So we're going to round this and say he can sell about 175 items. Remember that these are estimated values based on a linear regression or a trend line, so they're not precise. It's not guaranteed that with 11 advertisements he will sell exactly 175, but that's the best estimate that we can make based on the data we have. So that pretty much covers it. If you're going to do more regressions, always clear out your calculator in between. So you can either click the little X's by each row or click on the gear and click delete all. So if you feel like you've got it, then that's all for notes. I'm going to go ahead and do one more example. If you're not feeling comfortable, I'm going to do this horizontal table with age and height, and we're going to find the equation and the correlation coefficient for that one. So yeah, we're going to do a new table. Our x values are 2, 3, 3, 4, 4, 4, 5, 5, 5, 6. And our y values are 30, 33, 34, 37, 35, 38, 40, 42, 43, 42. So again, we'll use this magic button. It creates a linear regression. So we come up with an equation that we can write. Again, it doesn't tell us what to round to, so we'll go with the nearest hundredths again. Y equals 3.46x, because we have 457, so it rounds up to 0.46, plus 23.22. That does not bump up because the next number is a 4, so we don't need to round it up. Then our R value, our correlation coefficient, it's not part of the linear equation. It's a separate value. And the R value is 0. Since this one is smaller than 1, we don't want to keep just 2 numbers, so we're going to go to the thousandths place again and do 0.94. The last number is a 5, and since it's followed by a 7, we'll bump it up to 6. So we have a 94.6% correlation between these two things, which is, again, a strong and positive correlation, just like the last one that we did. So there's 2 more examples here. There's more examples on the practice page down here in OneNote. So use those as practice, and as you're working in Delta Math, make sure that you're using Desmos as your calculator so you practice it. Don't use the Delta Math statistics calculator. Use Desmos and use the Texas version to make sure that you're practicing the right thing.